Hi everyone! In this video I want to do a brief overview of basic machine learning approaches and ideas behind them. There are several families of machine learning algorithms which I want to review. It's a linear model, tree-based methods, nearest neighbors and neural nets. For each of this family I will give a short intuitive explanation with examples. If you do not remember any of these topics, I strongly encourage you to learn it using links from additional materials. Let's start with linear models. Imagine that we have two sets of points. Gray points belong to one class and green ones to another. It's very intuitive to separate them with a line. In this case, it's quite simple to do, since we have only two-dimensional points, but this approach can be generalized for a high-dimensional space. This is the main idea behind linear models. They try to separate objects with a plane, which divides space into two parts. You can remember several examples from this model class, like logistic regression or SVM. They all are linear models with different loss functions. I want to emphasize that linear models are especially good for sparse, high-dimensional data. But you should keep in mind the limitations of linear models. Often, points cannot be separated by such a simple approach. As an example, you can imagine two sets of points that form rings, one inside the other. Although it's pretty obvious how to separate them, linear models are not an appropriate choice and will fail in this case. You can find implementations of linear models in almost every machine learning library. Most known implementations are in scikit-learn library. Another implementation which deserves our attention is Walpole-Webbit, because it's designed to handle really large datasets. We finish with linear model here and move on to the next family, tree-based methods. Tree-based methods use decision tree as a basic block for building more complicated models. Let's consider an example of how decision tree works. Imagine that we have two sets of points similar to a linear case. Let's separate one class from the other by a line parallel to the one of the axis. We use such restrictions since it significantly reduces the number of possible lines and allows us to describe the line in a simple way. After setting the split as shown at the picture, we will get two subspaces. Upper will have probability of gray equal to 1, and lower will have probability of gray equal to 0.2. Upper subspace doesn't require any further splitting. Let's continue splitting for the lower subspace. Now we have 0 probability of gray for the left subspace and 1 for the right. This was a brief overview of how decision tree works. It uses divide and conquer approach to recursively split spaces into subspaces. Intuitively, single decision tree can be imagined as dividing space into boxes and approximating data with a constant inside these boxes. The way of choosing the splits and corresponding constants produces several approaches for building decision trees. Moreover, such trees can be combined together in a lot of ways. All this leads to a wide variety of tree-based algorithms, most famous of them being random forest and gradient-boosted decision trees. In case if you don't know what is that, I strongly encourage you to remember these topics using links from additional materials. In general, tree-based models are very powerful and can be a good default method for tabular data. In almost every competitions, winners use this approach. But keep in mind that for tree-based methods it's hard to capture linear dependencies, since it requires a lot of splits. We can imagine two sets of points which can be separated via a line. In this case, we need to grow a tree with a lot of splits in order to separate points. Even in such case, our tree can be inaccurate near decision border, as shown on the picture. Similar to linear models, you can find implementations of tree-based models in almost every machine learning library. Scikit-learn contains quite good implementation of random forest, which I personally prefer. Although scikit-learn contains implementation of gradient-boosted decision trees, I prefer to use libraries like XGBoost and LightGBM for their higher speed and accuracy. So here we end the overview of tree-based methods and move on to the KNN. Before I start the explanation, I want to say that KNN is abbreviation for K nearest neighbors. One shouldn't mix it up with neural networks. So let's take a look at a familiar binary classification problem. Imagine that we need to predict label for the points shown with question mark at the slide. We assume that points close to each other are likely to have similar labels. So we need to find the closest point, which is displayed by arrow, and pick its label as an answer. This is how nearest neighbors method generally works. It can be easily generalized for KNN if we will find k nearest objects and select class label by majority vote. The intuition behind KNN is very simple. Closer objects will likely to have same labels. In this particular example, we use square distance to find the closest object. In general case, it can be meaningless to use such distance function. For example, square distance over images is unable to capture semantic meaning. Despite simplicity of the approach, features based on nearest neighbors are often very informative. We will discuss them in more details later in our course. Implementations of KNN can be found in a lot of machine learning libraries. I suggest you to use implementation from scikit-learn, since it uses algorithmic tricks to speed up calculations and allows you to use several predefined distance functions. Also, it allows you to implement your own distance function. The next big class of model I want to review is neural networks. Neural nets is a special class of machine learning models which deserve a separate topic. In general, such method can be seen as black box which produce a smooth separating curve in contrast to decision trees. I encourage you to visit TensorFlow Playground, which is shown on the slide, and play with different parameters of the simple feedforward network in order to get some intuition about how feedforward neural nets works. Some types of neural nets are especially good for images, sounds, text, and sequences. We won't cover details of neural nets in this course. Since neural nets attracted a lot of attention over the last few years, there are a lot of frameworks to work with them. Packages like TensorFlow, Keras, MXNet, PyTorch, and Lasagna can be used to fit neural nets. I personally prefer PyTorch, since it provides flexible and user-friendly way to define complex networks. After this brief recap, I want to say a few words about no free lunch theorem. Basically, no free lunch theorem states that there is no methods which outperform all others on all tasks. Or, in other words, for every method we can construct a task for which this particular method will not be the best. The reason for that is that every method relies on some assumptions about data or task. If these assumptions fail, the method will perform poorly. For us, this means that we cannot win every competition with just a single algorithm. So we need to have a variety of tools based on different assumptions. Before the end of this video, I want to show you an example from scikit-learn library, which plots decision surfaces for different classifiers. We can see that type of algorithm have a significant influence of decision boundaries and consequently on answer. I strongly suggest you to dive deeper into this example and make sure that you have an intuition why these classifiers produce such surfaces. In the end, I want to remind you the main points of this video. First of all, there is no silver bullet algorithm which outperforms all the other in every task. Next is that linear model can be imagined as splitting space into two subspaces separated by a hyperplane. Tree-based methods split space into boxes and use constant predictions in every box. KNN methods are based on the assumption that close objects are likely to have same labels, so we need to find closest objects and pick their labels. Also, KNN approach heavily relies on how to measure point closeness. Feedforward neural nets are harder to interpret, but they produce smooth nonlinear decision boundary. The most powerful methods are gradient-boosted decision trees and neural networks. But you shouldn't underestimate linear models and KNN, because sometimes they may be better. We will show you relevant examples later in our course. Thank you for your attention.